Okay, so question 7, it says consider the balanced redox reaction. So this one they give us here in 7.1 was balanced. And then the first question is to define oxidation, and usually for this they will specify in terms of what, like they'll say define oxidation in terms of oxidation number, or they'll say define oxidation in terms of electron transfer. Do you know both the definitions?
Think so.
All right, so what does the electron transfer one say?
Oxidation is the loss of electrons.
Yes, exactly, that's it. And then the oxidation number one?
It's the increase in oxidation number.
Yes, definitely. Then reduction would just be the vice versa of both those definitions. Then they say from the balanced equation above, write down the reduction half reaction. And then if they give it in this way, you can always go and confirm your half reactions on the standard reduction potentials. You'll see that you are going to end up with Cu becoming Cu2 plus and plus 2 electrons, and then the other one will just be Ag plus becoming Ag plus an electron. Okay, the electron will be on the other side, sorry, so let me just move that to wait. So if the question was for this two, wait, let me just go back. I'm still kind of getting used to this new release of the app. Just updated it. Okay, so the electron will be on this side. If they ask you between these two half reactions, which one will have a higher E naught? Like which one will have a higher E naught, like this, just looking at the equations, I mean, or just looking at the half reactions.
Copper.
Okay, why copper? Remember the standard reduction potentials. Standard reduction potentials always give you the half reaction in terms of reduction, in terms of the gaining of electrons. So we say that the one that stays reduction, this one is reduction, is the one with the highest E naught. So that issue that we had on Saturday is still a problem a little bit. But I really want it to not be a problem, because according to me, it's supposed to be the easiest work in all of chemistry. The one that stays reduction like this is supposed to be the one with the highest E naught. You can go and confirm this, and we'll see that Ag is all the way up here. You can see Ag is here. Wait, doesn't want to write now. Okay, here is Ag. The E naught is plus 0.80, and then here is Cu 2 plus 2 electrons. The E naught is plus 0.34. That's why we see Ag becoming exactly the way it was, because it has a high E naught. Then copper swaps. In the table itself, it was given like this in terms of reduction. That's why we call the tables standard reduction potentials. It was given like this, but because it's overpowered by the strongest oxidizing agent, which is Ag plus, it's gonna have to swap directions. It's gonna have to flip and look like this. So now it becomes oxidation, because Ag is gonna keep the reduction. I'm not sure if this makes sense. Does it make sense?
Yes.
Yes. I just want you guys to just try to go back and watch the recordings. It's always a song that I sing, but I really wish you can listen to what I say. It's gonna be important for you to remember this. It's just one thing that you have to remember, but I can tell that it's still not like comfortable. You're still not comfortable with this. Okay, but anyways, we have the half reactions. Then they will obviously ask for the reducing agent, and then our reducing agent, every time you see the word agent, you remember that it has to be vice versa. So if it's a reducing agent, you are basically looking for the one that is oxidized, isn't it?
Yes.
Yes. So which one is oxidized in our half reactions?
The copper.
It's the copper. Yes. So that's our reducing agent. And once again, you always pick the first thing that appears on the reactant side. So in this case, Ag plus will be our oxidizing agent because it's the first one that appears on the other side, on the reactant side. Sometimes you do have, you see this half reaction that includes chromium. It's gonna have a bunch of things here like H pluses and stuff like that. But when they ask you which one is the oxidizing agent or reducing agent, you're just gonna go ahead and pick the first one that you see on the reactant side. That's it. Then you make sure that you get that 1 mark or 2 marks. Okay. Then the next question is explanation for the answer in 7.1.3 referring to the oxidation numbers. Then they just basically wants you to explain what oxidation is, because a reducing agent is oxidized and something that is oxidized will have an increase in oxidation number. So we just picked copper. Let's now prove it. Copper in the reactant side has an oxidation number of 0. And then copper on the product side, it is an oxidation number of +2. So we can definitely see that copper. So you're going to say this first, and then you can say that therefore copper is oxidized. Then if copper is oxidized, you conclude by saying then it is an it is a reducing agent. Okay, yeah, that's it. Then we go to 7.2. It says the following incomplete chemical reaction represents a redox reaction. Yes. Then the first question is determine the oxidation number of Cr in CrO7 2 minus, and we did this one quite a lot. I think it will always come down to like +6. You can check that as well. But 7.2.2, which I want to focus on, says using information from the table of standard reduction potentials. These tables have no different name. It's always going to be called standard reduction potentials, because everything is given in terms of reduction. Every electrons that are there on the table, whether it's 4A or 4B, they are added on the reactant side. They are gained. So we're just going to look at the one with the highest E naught and keep it the way it is. That's it. But in this case, they just want us to write down the balanced net ionic reaction, clearly indicate the half reactions and the final balanced ionic equation. So this goes for all balancing questions. You just go and look at your reactant and your product that is related to that reactant. Same applies to this other reactant. You look at its product, then you can tell that, okay, chromium 2O7 2 minus goes on to become chromium 3 plus. So in your half reactions, you should look for those two things. There's going to be some other things that are added, but the key is to look for these two. If those two are not represented the way they are, then it's not the correct half reaction. I'm not sure if I'm making sense.
It makes sense.
All right. Same applies to the Fe. If you don't see Fe2 plus becoming Fe3 plus, then you know that you're not picking the right formula or the right half reaction. And remember, this will be written in terms of reduction, so you expect it to be flipped when you check it. But once again, the key is just to check Fe2 plus and on the other side Fe3 plus. That's it. So let's go ahead and check. First we'll check for Fe2 plus and Fe3 plus. Then we'll circle that half reaction and then we'll go and check the other one. And then that will be a little bit quick. This might appear very small on your side, but hopefully you can zoom in a little bit just to check the other ones. But there is the Fe3 plus and the Fe2 plus. Do note that there is definitely some more Fe reactions that will be there. The one that I'm highlighting in red right now is also on Fe. The one I'm highlighting again in red is also on Fe. So there's a couple of them. Maybe it's not only these three. So what you have to do is to check exactly the oxidation numbers that you have or the charge. So that one in green will be the correct one because these two in red end up being Fe on the other side instead of either Fe2 plus or Fe3 plus. Okay. So we just picked out that one. We write it out nicely. Fe 3 plus, I mean that's 3 plus an electron becomes Fe 2 plus. Then I go up and check the chromium one. Just remember we are looking for chromium 3 plus and Cr2O7 2 minus. So I'll go ahead and highlight that one in yellow. I'm sure you can already see it up there. Everything that you're looking for is there. Cr3 plus is there. Cr2O7 2 minus is there as well. And then the one that I'll highlight in red is not the correct one. Sometimes it's not easy to identify which one is not correct. I've seen a lot of examples where even myself I'm confused. But it seems like for Cr it's easy because this other one in red, it does not have oxygen in it. So that's pretty easy to identify. But if you look at, for example, this one, you see this MnO2, and then also check it against this one here, MnO4. They are very similar, those ones. They are very, very similar. So you can easily get it wrong. So should be extra careful to pick out. If they say MnO4 minus, make sure you pick that out. If they say MnO2, make sure you pick that out. Okay, is that good?
Yes.
All right. So I'll write the E naught of the Fe. E naught is equal to plus 0.77, and then I'll also copy out the Cr1, Cr2O7 2 minus plus 14 H plus 6 electrons. This is just me writing it out the way I find it in the table. 2 Cr 3 plus 7 water molecules. And then the E naught of this one is plus 1,33. So looking at these two half reactions, which one will stay the same? Which one will stay the way it is?
The first one.
The first one, yes, exactly, because the E naught is larger there. So then the second one has to flip. I'll then write it this way. Fe 2 plus becomes Fe 3 plus 1 electron. And once again, this is confirmed also by the question paper. You can see they have Fe as the reactant, Fe2 plus and Fe3 plus as the product, because that also agrees with the table. Okay, then now for the balancing, which one do we need to multiply and by what?
Multiply the Fe with 6.
Yes, exactly, and that's it. We just multiply this whole half reaction with 6, and then that gives us, I can just go ahead and write the final net ionic reaction. Yep. So it's going to be Cr, doesn't matter which one I start with, Cr2O7, 2 minus, and then I'm just gonna, I don't know if I'll have space, but I'm just gonna add everything, plus 14 H plus, then it's gonna be 6 Fe 2 plus, and then this becomes 2 Cr 3 plus 7 water molecules plus Fe, it's gonna be 6 Fe 3 plus. After balancing my electrons, then everything now should be nice and correct. Once again, remember, you have to check two things after you write your net ionic reaction. First, you check if every element is balanced. That one should be quick, so we can check our Cr here. There is 2, there is 2 on the other side. Our oxygen, there is 7, also 7 on the other side. Our H pluses, or H, is going to be 14. This side 7 by 2 is 14. Fe is 6. Fe is 6. So the elements are balanced. Another quick thing to check. Or do you remember another thing to check if it's balanced?
Does it involve using the charge?
Yes, we check the overall charge. So chromium, or the first compound, is going to have -2. The second one is +14, because it's 14 times 1. And then the next one is 6 times 2, which is +12. Then I go to the other side and say I got 2 times 3, and that's +6. I got 7 times 0, that's a neutral, so it's fine. I go and say 6 times 3 is 18. Then I'm just gonna add now. So -2 plus 14 is 12, plus 12 is 24 on this side, positive. On this other side, 6 plus 18 is positive 24. So also the charge is balanced. Now I know for sure that I did a correct thing. Okay. But you should be sure that if you're using the tables, then once you balance the electrons, automatically everything should be balanced, as long as the electrons are balanced and then you used the correct formulas from the tables, should be good to go. All right, any question?
No.
No questions. Okay. Is this the kind of work that you've been doing maybe at school?
Yes.
Okay, how was it when you were first doing it?
The example was confusing, but as I did it, it wasn't that hard.
Yeah, This table is it's like the memo. According to me, it's the memo, because if you try to balance these things out by yourself, it's impossible. Like, I know exactly how to balance this half fraction. You see the way it was given. If I just go a little bit back here, only given this two, so it's quite difficult to even balance the oxygens. But yeah, using the tables, it's easy. You just pick it out. As long as you make sure you pick the correct things, should appear exactly the way it is written out on either side. Okay. What is the time on your watch?
Sorry, glitching.
It's, say that again.
No, you were glitching.
Oh, I was asking what is your time on your watch or phone?
17:30.
Okay. So I think we are done with this one. So let me save this recording actually.